Hello, I hope you guys are okay. It's been a while since I've made any video tutorial. I've been a bit busy, but now I'm trying to get back on track and I have some very interesting ideas related to machine learning, data science, and I'm even thinking to make a video tutorial related to some hardware project, right? So something related to robotics or IoT and stuff like that. And okay, let's begin today's tutorial. So today we will be working on machine learning, and today we will write a code for linear regression using gradient descent algorithm. So something very simple and very basic. If you're beginning to learn machine learning, this is one of the very basic and very important algorithms. We will write the code, step-by-step code from scratch in Python, obviously. So that means we won't be using any library or module to implement linear regression. For example, we won't be using sklearn or any other library or module. Because if we use a library or a module, what we have to do is, for example, if you use sklearn, what you will do is you will just arrange your data set, right? And then you will call the function, the respective function. For example, for regression, we will call the regression function or any other variant of regression function. So although it sounds more simple, more easy, right? But what happens is that function does everything for you. It does the work for you. And you don't understand the underlying concept which that function is doing for you, right? So it may be good for you if you are not a beginner. If you are a beginner, you are trying to understand the algorithm, it is better to implement linear regression or any other algorithm without using that function. And it's not that hard, it's very easy, very simple. We'll see that quickly. And maybe we can do another tutorial in some other time in which we will use the libraries to implement the same algorithm, right? Okay, now let's begin. And before coming towards the code, let's quickly understand what is linear regression, right? We will quickly see it and try to understand the concept, and then we will start writing the code. So that when we are writing the code, you know what's happening, you know what we are doing. Let's say we have a data set that has two variables, x and y. For every x, we have a y. X is the independent variable, while y is the dependent variable. And y is the variable that we are predicting. We have to predict it, right? And in machine learning terms, we call it as label or class or simply the output variable. So in regression, we can call it the output variable. Okay, and we could have many x variables. For example, we could have x1, x2, x3, and so on, many variables, and we would have called them as feature variables. But for simplicity, we have just used one variable here, and this is the feature variable. Now let's suppose if x is 2, y is 4, x is 3, y is 6, x is 4, y is 8, and so on. Now we can plot these points. Let's say this is the x-axis and this is the y-axis, right? Okay, I'm gonna roughly plot them. I'm not gonna plot them by mapping them exactly. I'm just gonna do it roughly. So maybe these points they lie somewhere like this. Right, let's suppose there are many other points in this data set. They are lying on the plot or the map, something somehow like this. All right, you can actually see a pattern here in these points. Now, what is linear regression? So linear regression actually attempts to map this relationship between the variable x and the variable y, and it does so by using an equation, or in other words, a line. So if you try to map a line here, if you can represent this data set with a line, what will that line be? It will be somewhere like this. if I map these data points, if I map it using a line, I will put it somehow like this, right? I won't put it like this or this. These are the wrong representations, right? This one will be the right representation. So if I want to represent it using a line, I will put the line somehow like this, right? So this is actually linear regression. Linear regression attempts to tell us a relationship between x and y by plotting a line, a line which represent this data in the best possible way. And now when we talk about the line, you know, every line has an equation, right? Every line has an equation, and we know the equation. You must have read it in your school maths. That was y is equals to mx plus c. We can represent any line with an equation. If we talk about this equation, y is the output variable, x is the input or the feature variable, m is the slope. Slope means how tilted this line is. So each of these lines have a different slope. You understand what is slope, right? And c is the y-intercept. So actually, linear regression attempts to model the relationship between two variables, that is the variable x and y, by fitting a linear equation to this observed data, right? So when we say we are training our model, we are actually trying to learn the right values of these variables m and c, right? We are trying to learn the right values so that in future when a new value of x comes, we can find the right value of y for it, right? So in future when we have a new input variable, we know the output for it. We can predict the output. That's how we do it. So if you talk about in terms of line, if you talk about it in terms of line, if a new value of x, for example, let's say a new value of x comes here, we can simply, if we know the line, if we know the correct line, we can simply map it and find the right value of y from it. For example, let's say here, I know this line is not straight. Let's just assume this is straight. This is just for understanding. I couldn't draw it a straight line. Maybe it would have gone there otherwise. So you understand the concept. This is what linear regression is, and we will write the code, and our code will actually be trying to find the correct values of m and c, and we will be using two variables. So if we have two variables, the equation becomes y is equals to, let's say, m1 x1 plus m2 x2 plus c, and you can do it for as many variables as you want. So in our code, we will be trying to find the values for m1, m2, and c. Let's quickly understand what is gradient descent, and then we'll look at its pseudocode. To understand gradient descent algorithm, we need to look at the plot of loss and weights, right? So loss is actually the difference between the actual value of y and the predicted value of y. Y is the variable that we are predicting. So loss is actually the difference in our prediction, right? So we have many kinds of losses. We have different equations we have different loss functions, and I'll talk about it in a while. Now, what are weights? Weights are the coefficients m and c, y-intercept, right? So if we have multiple m, all of them come under the weight category. They are the weights. Okay, before looking at this graph, I think you should consider this image. So here you can see that we have two mountains, and this is the minima point between these two mountains, and this is your goal. You have to reach this place, and you are placed randomly anywhere. Maybe you are standing here, right? You are standing here and you have a blindfold on your eyes. You don't know in which direction you have to go, and this is your goal. So if you are made to stand here with a blindfold on your eyes and you don't know the direction, and you have to reach the minimum point on the ground, the minimum point on the mountains, or wherever it is, right? So what will you do? It's something like this. Right, so what will you do? Obviously you will move and you will look for the slope, and you will try to understand where is the slope um, going downwards, right? So you'll feel with your feet probably that uh, in which direction you move will take you downwards, because you need to reach the minimum point, not the highest point, right? You understand, you get it. So since you need to move to the minimum point, you will move towards that direction of slope that will take you downwards. So now, keeping that in mind, let's come back to this plot. This is your goal. This green point is your goal. This is where the algorithm has to reach. And this is where it is present right now. This is where it is right now. And how does it know it has to move in right direction or the left direction? And we know that, through maths, through mathematics, that the slope of this line is positive, right? And the slope of this line is negative, right? Slope of this line is positive and this one is negative. So when you are standing here and the slope is, this, what will be the slope of this line? Obviously negative. The slope of this line will be negative. So if you are standing here, you know that you need to move in this direction. This is your direction. And if you're standing here, let's say this is where you are present right now, right, this point. And if you're present here, you know that your slope will be positive. You can find the slope wherever you are, you can find the slope. So this will be positive. So if it is positive, this means you have to move in the left direction, right? So that's how you will reach this point. And when the slope is 0, it will definitely be 0 when once you reach here, the slope of this line is 0. So when it's 0, you will know that you have reached your goal point, right? So using the sign of slope, we know where to move. So this red point here, this red point is actually the weight, the values of M and C, and we need to update those values depending upon the sign of the slope, right? So and why do we need to move towards this minimum point? Why are we not moving towards this maximum point? Why? Because this is the point where the loss is minimum, and obviously we need to minimize the loss, right? We need to minimize it so that our predictions are more nearer to the actual values of y. So we need to minimize it. So for that we need to reach the minimum point, and for that we update our weights, the values of M and C, the coefficients. And how do we do that? Using this using the sign of slope. And you also know that slope is actually the gradient or the derivative. So what we actually do is we have a loss function, right? This loss function, and we find the gradient or the derivative of this loss function with respect to the weights, with respect to M and C. Now let's look at the loss function that we are going to use to implement in our code. The loss function that we will be using is mean square error, and it's very simple. Let's look at its equation. So first of all, what we do is we find the difference between the actual value of y and the predicted value of y, right? And by the way, for prediction, we use this equation, y is equals to mx plus c, and you already know that. We've seen this equation in a little while ago in the same video. So we find the difference between actual y and predicted y for a particular value of x, and then we square this difference, hence the name square. And then we find the mean. We find the mean of squares of all the values in the data set, right? So hence the name mean square, and the equation becomes this. This is the equation. So why do we square the difference? Why? There's a very good reason for it, because let's say, let me find the pen. Yeah, let's say one error is, let's say, -4, and there is some other error which is +4. Maybe this is the case. If you add them, what will you get? 0. So the algorithm will think that there are no losses. Your prediction is perfect. It's exactly like the actual y, but that is not the case. You have a big difference, right? So to avoid this kind of situation, we just square all the losses, all the differences. So if you square them, it won't then amount to 0. It will not be 0. So we do that. And by the way, you may think that if we square it, maybe if the loss is, let's suppose 2, maybe if you square it, it will be 4. So it will actually increase while we want to decrease the loss. So why do we square it? One reason is this is what I told you. And secondly, there is no harm in doing this because we just need to minimize the loss, right? So if we minimize, whether we minimize 4 or whether we minimize 2, doesn't make much of a difference, right? Our goal is to minimize it. So even if we square it and then try to minimize, it doesn't make much of a difference, right? And why do we do it? I just explained why, because it may amount up to 0 if we add them, and there are same losses of different signs. Now that we know that this is our loss function, we just learned a while ago that to find slope, we need to get the derivative of this loss function. So what is the derivative of this loss function with respect to the weights? That is derivative of this loss function with respect to m and with respect to c. We will get two different equations. Let's see what is that. The formula for the derivative of loss function with respect to m is this one, and with respect to c, or the y-intercept, is this one. I've just written b instead of c here, so don't be confused by that. And you know this is actually the predicted y, mx plus c, or in this case I've written b, so mx plus b. So this is the predicted value of y, and this is the actual value of y. I'm not deriving these two equations right now. If I do that, this video will be very long, so I'm not going to do that for now. We'll just use this formula and implement it. Okay, so one more thing. What does this summation means? It means that we have to find the value of this equation for all the values of x, and then we'll sum it up. So let's say this is our x, and we have, let's say, three different values of x. So what we will do is we will put the first value here and find the answer, and then the second value, and then the third value. So with all the three values, we'll get three different answers, and then we will sum up all those three different answers. This is not 0, this is just the space for some value, right? So assume this is some value. So we will add up all the three values, and then we will divide by n. N is the total number, right? Okay, I'm going to implement it and you'll understand it better then. Let's see. The pseudocode for gradient descent algorithm is, first of all, we initialize the coefficients with random values, right? It's better to start them with random values instead of 0 values. It's better that way. After initializing, we start the loop, and then we calculate the predicted output, and then we have to find the derivative of the slope, right, with respect to the coefficients. Then we update the coefficients, and we use these new coefficients for the calculation. That means we start the loop all over again using the new coefficients, right? And how do we update the coefficients? There is a formula for that. Let me show you. After showing this pseudocode, let me show you how to update the coefficients. It's actually let's see, if you have m, you update it with the m minus the learning rate into the, I think, derivative. This is how you do it. I'll show you too after this. Okay, and then we repeat the loop until either the dataset is iterated, that means we have iterated the dataset for like many times and there is no more room for improvement. So either that or the loss stops decreasing. So again, there is no room for improvement when the loss stops decreasing, right? Or we achieve a particular level of accuracy that we need. and then we stop it. This is the formula for updating the coefficients. M equals to M minus learning rate into the derivative of loss function with respect to M. And the same is the case for C. The difference is the derivative is different now. It is derivative of loss function with respect to C. Learning rate is, by the way, how fast we are moving. How fast we are moving towards our goal. And we try to have a larger learning rate when we are quite far away from the goal, and we tend to have a smaller learning rate when we are nearer to the goal, so that we don't miss the goal. Let's start our implementation. We'll begin by loading our dataset first, and for that obviously we need pandas. All right, I'll also use numpy, so let's import that, and matplotlib. Okay, so this one is for plotting the loss function, and I'm also thinking to do some animation. Let's try that, and for that we need this. All right, now let's import our dataset. First feature that we are using is the ground living area. The second feature we are using is total basement surface area, and our output variable is the sale price. All right, now we have got all these in these variables. Let's see what is the output, so that you know what is there in x1. All right, let's standardize them first, and then we'll move forward. So I'm just using the formula for standardization. Same goes for x2. Now we have the two features here in two different variables. What I want is I want to concatenate them together to make a matrix out of them, so that I can write vectorized code. Right? Let me show you what I mean. This is x1, and it has 3 values, and then I have x2, which has some other 3 values. What I want is I want to convert them in a matrix, and I want to write these values here like this. Right, so that just like they were there in Excel, as they were present in the dataset in Excel file. So this will be my first column, and this is my second column. Now for this we have a function in numpy, and using that function I'm gonna convert these two variables like this. Right, how will this help me, and how will I use them later? I'll tell you that in a while. Also, I will also append a column of ones here in the matrix. So this will be my matrix, and I will explain this in a while, but I'll just tell you that this is for, remember the equation? We had m1 into x1 plus m2 into x2 plus c. So this 1 is for c. The c is the y-intercept, by the way. Right? You will see how is this helping me, how adding this one column is helping me. You'll see that in a while. I will also show you that here. So I have a variable, let's say this, and I have another variable. By the way, if you're writing some code and then you get confused by some complex function of some library or some module and you want to test it out, the best way to do it is just open up Python shell and write your code here and just run that function once with some simple array or list or anything, a simple version of whatever you are doing, and it will be very easy to understand. Now look at it. I have x and y. I'm going to concatenate them together like this. Let's see the output. Okay, I didn't import numpy here. Yeah, I'm going to write the same code again. So you see these two arrays or lists, you can say they are appended here like this. So I'm going to use the same function again on our feature variables. Let's do that. And also I will add a list of ones. We have a function ones in numpy. And how many ones do I want to add? I want the size should be the same as the size of x1 or x2. Number of rows, number of rows should be the same as the rows of x1. So that's why we're writing this. Okay, looks good to go. And let's see the output as well. So this is my first feature, this is my second feature, and this is for y-intercept. Let's also check out the shape. Okay, now let's write the code for gradient descent. I'm keeping it constant for now. This is the step size. How many epochs or iterations do we want? Let's keep 2000 for now. You can change it, by the way. Okay, what is the size of our dataset? What are the number of rows? These are the number of rows or number of examples in the dataset. Okay, we want some random values for the coefficients, right? By coefficients, I mean the slope, m1 and m2, right? The coefficient. So, first of all, I'm gonna add a seed for random number generation. You can add any other number here as well, of course. And let's write coefficients is equals to it will generate 3 random numbers, and we have 3 coefficients, right? We need 3 coefficients. We need m1, we need m2, and we need c. So these are the 3 coefficients. That's why I written 3 here. All right, let's print these as well. we have to send it x, y, coefficients, epochs, and learning rate. Okay, let's initialize these two empty arrays. By the way, I came home today and I still haven't talked to my cute little robot. She's right here beside me. Alexa? Alexa? How are you feeling today?
Terrific. Thank you. Have a wonderful day.
It's night, Alexa. Okay, where were we? Yeah, we were initializing an empty array of coefficients. I don't know why I keep calling it array. It's a list, obviously. This is Python, not C. Okay, now let's start our loop. And how many times do we want to run the loop? Obviously, epoch times, right? How many iterations do we want? Epoch times. Okay. Now there comes the first step. And you're gonna be amazed by this. If you haven't used numpy before, you will really be surprised by this function. Okay, so we have a function dot, numpy dot, right? And what it does is, let me show you. Now this function numpy dot, it will multiply the values present in this array coefficient with the respective values in x, and then it will add them. And that is our prediction. So what we mean here is, this is our matrix. And this is the column of ones. This is x. The first column is for x1, the second is for x2, and the third is for c. And let's say our coefficients are a, b, and c. So what the function numpy dot will do, it will multiply a with 1 plus b with 4 plus c multiplied by 1. And then it will form the function of summation and add them all up together. So that was actually our formula. Y equals to a x1. We can write m1 or a, that's fine. B x2 plus c, and you can see c is being multiplied by 1. That is the reason we added this column of ones here, right? So it doesn't matter if c is being multiplied to something, because that thing is 1. So c multiplied by 1 is 1. So this is the formula for linear regression. This is our formula for a line, right? So this function actually multiplies with the respective values, and then it adds them all up. It does the function of a summation, and we will use this function numpy dot again in the coming code. So remember how it works. To understand it better, let's look at this code. Now let's use this function numpy dot. It basically works like a dot product between two matrices, or a matrix and a vector. So you can see 1 was multiplied to 1 plus 2 was multiplied to 2. That means 4. So 4 plus 1, 5, and so on. So right now there are 3 rows in this list. There are 3 rows. So the result, of the rows of the result was also 3. So right now we have like 1500, some 1400 something values in our data set. So with the use of one function, all of those 1400 values will be added, will be multiplied, added, and we will get 1400 something results, 1400 something predictions. So with the use of just one function. So this is vectorized coding, and by the use of this I just avoided a for loop. I would have used a for loop if I wouldn't have used this function, and it's really fast and obviously efficient. Okay, coming back to our code. Okay, now let's calculate the error in our prediction. That will be prediction minus y, the actual value of y that was stored in y variable here. We know the cost function. We have the formula for cost function. We're going to use that formula, and using that was 1 over 2n, n is the size of our data set, multiplied by square of error. So we are using mean squared error, right? So it is square of the error. So again, for square, I'm going to use the dot function again. Why is that? I can use numpy.square, but that actually doesn't sum up the error. It will just square every value in this list. But you know, for this function, the cost function or the loss function, which is we are using mean squared loss function, the formula is summation of the squares of all the squares, summation of all the squares of the errors or the losses. So we need summation as well, and dot function sums up as well. That's why we won't use square, we will use the dot function. So I'm using transpose because obviously you know you can't multiply, this is a list, 1D list. You can't multiply two lists with this function. The dimensions won't match. So I'm making it transpose. You can do that on a paper if you want to understand it better, and if you are unable to understand it. So the first value of error, when it's in transpose, when it's a transpose, the first value will be multiplied to the first value of this. This is what I will write. So the first value of this list will be multiplied to the first value of this list, and they both will actually be same. That's why it will calculate the square. If you still don't understand, let me know. I'll explain it in more detail. And then we will append the cost. And now it's time to update. First of all, we will find the derivative, and then we will update our coefficients. All right, let's find the derivative. So for derivative, the formula was learning rate multiplied by 1 over n. Let's write 1 over n first. 1 over n multiplied by learning rate multiplied by the summation of, and again I'm going to use the dot function, summation of x multiplied by the error. So we have to multiply the x with the error, x the feature with the error. Again, I'm going to use transpose because the dimensions won't meet otherwise. So this error is y predicted minus actual y. So this is in the formula. You can look at the formula. I have shown it to you in the same video previously. So you can look at the formula. This is just the formula, and numpy.dot will sum it up. Okay, so I think I've covered everything. Yeah, 1 over n multiplied by learning rate multiplied by dot product of this. Now let's update it. So coefficients equals to coefficient minus the derivative. Again, we have to append. We will append the past coefficients here. Why are we appending, by the way? We are appending because we need it to plot a line later on. And I'm going to write coefficient here. And then we will just get out of the loop and we'll just return. So there you go. Function is complete. Let's call it. This is the name of our function. We have to pass it x, y, coefficients, and what else? Learning rate. There you go. Now also let's display the last coefficient. We will display later. First of all, let's save the value of last coefficient in coefficient so that we can use it later on for plotting and predictions and everything. So in Python, if you wanna get or fetch the last value of an array, you don't know the index. We know the index right now. This is the size, so we can take the index from here. But if you don't know the index and you wanna find the value of last element of the list, you use -1 in Python. Now let's print our coefficients. Let's run this function and see the output. Let's see if it works. Okay, must have done some error somewhere. What did I miss? I didn't set epochs. I have to send epochs as well. And I have initialized the epochs, right? Yeah, here. Very good. This is NaN. Let me see. I've done something wrong, definitely. Okay, so I was supposed to append it here, and I'm just assigning it the last value. So it's not being appended, but that's not the problem. Okay, here I'm multiplying it. I'm doing the dot product here, but I haven't initialized it. So I have to put the first random value that we initialized it with here. This is the second mistake, so I have corrected two things. You should correct it in your code as well. This thing and this thing. Alright, let's run it again once. Yeah, I've done one more mistake as well. Yeah, so this is a big mistake. This was supposed to be x2. I have written the formula wrong. So change this as well. Let's run it again, and yes, our model is trained. These are the final weights. These were the first initial random weights, and these are the final trained weights. Okay, now let's plot the cost function. There you go. So this is our cost function. You can see that with the number of iterations, the cost has decreased, and after a certain number of iteration, it's not decreasing anymore. So it won't decrease any more than this with this linear function. So if you want to decrease your cost more, then we go for other kinds of regression, not linear regression, we go for exponential regression, or we change the formula so that it's more flexible. So our gradient descent code and our plot of cost function is complete. Let's create some animation for just for fun. So I've taken the code for animation from a source, and I will put the link of that source in the description below so that you can go over there, you can explore and understand. I have taken the code from there, and then I have modified it according to our problem. So I have already written the code. I will just copy from there and I'll paste it here. I have written it in another notebook and I tried it first before using in the video, so that's why I already have it. I'll just put it here and then you can see. So this is the animation code. So basically this code just creates an animation and then saves it with this name in the same folder as that of this code file, and it saves it with this name, and later on we will just play it. We will just open the file with this name and we will play it as a video. Here in this next cell we will play it as a video, and here in the code basically we are just plotting a scatter plot of the living area data points. We are plotting a scatter plot with red color, and then afterwards we are plotting our linear regression line. You can see that from here, using the coefficients, using all the past coefficients which evolved over time, right? So we plot the linear regression line one by one so that you can see how the line evolved over time. How did it set over the scatter plot? I'll just run this code and you will see how it's working. Okay, first of all, let's put the code for playing this animation here. I have already written that code. Let me just take it from there and put it here. So this is the code. Okay, let's run it first. So this code is still running. This symbol, this sign shows that it's still processing and it's creating our animation, and then it will put it there in the same folder. There you go. So this is our animation. You can see how the linear regression line is gradually setting on the pattern of the scatter plot. We'll do the same thing for the second feature. First feature was the living area, second one is the basement surface area. So we'll do the same thing for it, and let's see it. So this is the code for this second animation, the second feature. This is the complete code. This is the running code, and you can see the output. So this is the scatter plot for basement, and this is our regression line. I hope you guys learned something. It was a bit long tutorial. I hope it wasn't too hectic, and I hope you weren't bored. So do let me know how it was, and do let me know if you have any suggestions. I really hope you learned something. Anyway, thank you.